A stolen JSON web token is a permanent key to your user's data, unless your architecture actively invalidates it. Static tokens provide zero recourse once intercepted by a malicious actor during transit or via cross-site scripting. Stateless authentication relies on the server trusting the cryptographic signature without querying a database. While this improves scalability, it creates a security vacuum where tokens cannot be easily revoked before they naturally expire. Shortening the lifespan of an access token to minutes reduces the window of opportunity for attackers. However, frequent expirations force users to re-authenticate constantly, creating a friction point that destroys the user experience. Refresh tokens solve the friction problem by allowing the application to request new access tokens without user intervention. These are long-lived credentials stored securely and used only when the primary access token expires. Storing tokens in local storage exposes them to any malicious script running on your page. A more secure approach involves placing the refresh token inside a secure Hypertext Transfer Protocol-only cookie. Hypertext Transfer Protocol-only cookies are inaccessible to client-side JavaScript. This mitigation significantly reduces the risk of token theft through cross-site scripting attacks, as the browser handles the cookie automatically during requests. The same site attribute on cookies prevents the browser from sending tokens during cross-site requests. Setting this to strict or lax protects your users from unauthorized actions triggered by malicious external websites.
The secure flag ensures the cookie is only transmitted over encrypted connections. This prevents man-in-the-middle attackers from intercepting the refresh token while it travels across the network. Static refresh tokens are still vulnerable if the cookie is eventually compromised. Token rotation adds a layer of security by issuing a brand new refresh token every time the current one is utilized. When the client sends a refresh token to the server validates it, deletes it from the database, and returns a new pair of access and refresh tokens to the application. If an attacker steals a refresh token and uses it before the legitimate user, the server detects the second attempt as a reuse. This triggers an immediate security protocol to protect the account. Upon detecting reuse, the server must invalidate the entire family of refresh tokens associated with that session. This prevents both the attacker and the compromised client from obtaining further access tokens. A secure database schema for token rotation requires columns for the token hash, the user identification, the expiration timestamp, and a family identifier to link related tokens together. Never store refresh tokens in plain text within your database. Applying a strong hashing algorithm ensures that even if your database is leaked, the attackers cannot use the stored data to authenticate.
Unlike refresh tokens, access tokens should ideally be kept in the memory of the single-page application. This ensures they disappear when the browser tab is closed, minimizing the persistent footprint of credentials. A silent refresh happens in the background before the access token actually expires. The application uses a hidden fetch request to obtain new credentials without the user noticing any interruption in service. Implementing a request interceptor allows your code to check for expiration before every outgoing call. If the token is nearly expired, the interceptor pauses the request until a new token is retrieved. When an application programming interface returns a 401 unauthorized error, the client must attempt a refresh. If the refresh fails, the user session must be cleared and a login requested. Race conditions occur when multiple requests trigger simultaneous refreshes. The server must handle these gracefully, perhaps by allowing a very brief grace period where the old refresh token remains valid. A grace period of a few seconds prevents network lag or concurrent browser tabs from triggering the reuse detection logic incorrectly. This balances security needs with the realities of unstable network connections. The primary advantage of the access token is its stateless nature. The server only needs the public key to verify the signature, avoiding a database hit for every single authenticated request.
Standard claims like issuer, subject, and expiration provide necessary context for the token. Custom claims can include user roles or permissions, allowing the server to make authorization decisions locally and quickly. The audience claim restricts the token to a specific recipient.
This prevents a token issued for one microservice from being used to gain unauthorized access to a different, unrelated service. Using asymmetric algorithms like Rivest-Shamir-Adelman is superior to symmetric keys. It allows you to share the public verification key without exposing the private signing key. Just as tokens rotate, the keys used to sign them should also change periodically. This limits the long-term impact if a private key is ever compromised by an internal or external threat. JSON web key sets provide a standardized way to distribute public keys. Servers can fetch these sets from a known endpoint to verify signatures even after a key rotation has occurred. In a microservices architecture, the authentication service issues the tokens, while resource services verify them. This separation of concerns requires a centralized authority for public key distribution and revocation status. Revoking a stateless access token before it expires is difficult. One method is maintaining a short-lived block list in an in-memory store like Redis to check tokens against revoked identifiers. For high-volume systems, a Bloom filter can store revoked token identifiers with minimal memory overhead. While it has a small false positive rate, it significantly speeds up the revocation check.
Remember that the payload of a JSON web token is only encoded, not encrypted. Sensitive information like passwords or private user data should never be placed inside the token claims. Token binding links a token to a specific client certificate or secret. This ensures that even if a token is stolen, it cannot be used by a different client lacking the binding secret. Proper security headers, like content security policy, further protect your tokens. Restricting where scripts can be loaded from prevents the injection of malicious code that might attempt to exfiltrate credentials. A secure logout must invalidate the refresh token on the server side immediately. Deleting the cookie on the client is insufficient, as the refresh token would remain valid in the database. Each time a user logs in, a new token family identifier is generated. This allows the system to track distinct sessions across different devices and revoke them independently if one is compromised. Log every instance of refresh token reuse as a high-priority security event. Frequent reuse attempts from different Internet Protocol addresses suggest an active attack or a broad credential leak. The expiration of a refresh token should be absolute or sliding. Sliding expiration extends the session as long as the user is active, while absolute expiration forces a re-login after a set period.
Mobile applications handle tokens differently than browsers. Secure storage, like the mobile operating system keychain, should be used instead of standard file storage to protect refresh tokens from other apps. The patterns we are discussing are formal parts of the Open Authorization 2.0 framework. Specifically, the authorization code flow with proof key for code exchange is the modern standard. Proof key for code exchange prevents authorization code injection attacks. It uses a dynamically generated secret to ensure that the client requesting the token is the same one that started the flow. Manage your authentication state using a centralized store. This prevents different parts of your application from having inconsistent views of whether the user is currently logged in or refreshing. Always verify the issuer and audience claims on the server. Failing to check these allows attackers to use tokens from a different environment or a completely different application to access your data. Keep your token payload small to reduce network overhead. Large tokens are sent with every hypertext transfer protocol request, which can add significant latency to high-frequency application programming interface calls. Browser fingerprinting can be used as an additional check during token rotation. If the fingerprint changes significantly during a refresh, it may indicate that the token was moved to a different machine. Apply strict rate limiting to your refresh endpoint. This prevents attackers from brute-forcing token identifiers or overwhelming your database with a flood of malicious refresh requests.
Maintain an audit trail of token issuances and rotations. This data is invaluable during a post-mortem analysis after a security incident to determine the scope of data exposure. Signature validation must be the first step in processing any incoming token. If the signature is invalid, the request should be rejected immediately without processing any other part of the payload. Use a standardized library for token operations rather than writing your own cryptographic code.
proven libraries are less likely to contain common security flaws, like incorrect padding or timing attacks. Secure token rotation balances security and usability by combining short-lived access tokens with strictly managed rotating refresh tokens. Implementation requires careful coordination between client storage and server-side validation logic.